Hi, my name is Lorenzo Lupo, and this presentation is about encoding sentence position in context-aware neural machine translation with concatenation, a joint work with my two PhD supervisors. Let's start with an example to understand why context-aware neural machine translation is useful. Here I input this English sentence into the Google Translator, and I translate it into French. The system correctly translates especially this portion of the sentence that is ambiguous because it can be translated in two different ways according to the formality that we want to convey to our interlocutor. In this case, we're speaking with Mr. President, therefore the highest formality is needed, and the system makes the good translation. However, if we input into the same system the sentence split in two sentences, the system makes the wrong informal choice. And this is because the system is translating sentence by sentence independently from one another in a context-agnostic fashion. Therefore, when it is translating "are you," it cannot see Mr. President because it belongs to the past context, and therefore it cannot make the relationship. This tells us why context-aware NMT is useful and why we want to contextualize the translation of the sentences with all the available information in the other sentences belonging to the same document. Most existing approaches to context-aware neural machine translation restrict to use a few preceding sentences as context, because usually a few preceding sentences contain most of the disambiguating information that is relevant for context-dependent translations. In our work, we also restrict to this setting. The most straightforward approach to context-aware neural machine translation is by concatenation. So if we want to translate a document in the source language into the target language, here we have a document of 4 sentences, we can concatenate the current sentence that we are translating with its context into a unique sequence. In this case, we're only taking one past context sentence as context. Then we can input this sequence into the standard encoder-decoder architecture, which will be nowadays the transformer. The advantage of this approach is that we are not adding any extra learnable parameter to the standard transformer architecture, which we can train on also sentence-level data in a context-agnostic fashion. However, since we are concatenating many sentences together, attention can be distracted by the available context, instead of focusing on intrasentential linguistic relationships, which are the most relevant for language understanding and translation. Therefore, we propose to encode sentence position into token representations to make the model more aware of the fact that within the sequence that is being processed, there exist different sentences, and hopefully to focus more on the local linguistic phenomena that exist within each of these sentences. There are different ways for encoding sentence position into token representations. The first one that we propose to adopt are segment-shifted position embeddings. Segment-shifted position embeddings consist in a slight modification of the position embedding scheme. Position embeddings are usually sinusoidal and added to token embeddings at the input of the transformer. Positions go from 1 to the position of the last token in the sequence. In this case, we're concatenating 2 sentences, and the last token is at position 7. Segment-shifted position embeddings add a constant shift to the position of every token that belongs to subsequent sentences following the first one. So in this case, after we have encountered the separation token, we add a constant shift S to every position. If, for example, S is equal to 10, positions become 1, 2, 3 for the tokens of the first sentence, and then 14, 15, 16, 17 for the tokens of the second sentence. In this way, we made positions of tokens belonging to different sentences more distant from one another, and hopefully we're making the model more aware of the distance of the 2 sentences that belong to the process sequence. The second approach to encode sentence positions into token representations is by using sentence embeddings. Sentence embeddings consist in a further vectorial representation added to position and token embeddings. For example, in the BERT model, we have seen segment embeddings that were learned, but we can also use fixed representations such as one-hot encodings or sinusoidal embeddings. However, a natural question arises when we're using sinusoidal embeddings, which is whether we can distinguish position and segment embeddings that are both sinusoidal once they're added up together. For making them perfectly distinguishable by the model, we should probably concatenate these embeddings instead of adding them. However, this is an expensive operation because then it would require a projection back to the dimensionality of the model. To avoid this expensive operation, we propose to adopt position segment embeddings. The idea consists in reducing the dimensionality of position embeddings and segment embeddings to two dimensionalities DPE and DSE that summed up together are equal to the dimensionality of the model. In this way, we can represent in a vector of dimensionality D model position embeddings in the first part of the dimensions and segment embeddings in the second part of the dimensions. For example, if we use D model equal to 512, we could use 508 dimensions to encode positions and 4 dimensions to encode segment embeddings. We evaluate empirically the effectiveness of adding these sentence position encodings to the concatenation approach. In particular, we experiment with a 4-to-4 approach that concatenates 4 sentences and translated all of them in the target language. We experiment with 2 pretty diverse training and evaluation settings, both in terms of language pairs, availability of training data, and structure of the documents. We evaluate our systems with BLEU, but we know from the literature that BLEU is ill-equipped for measuring context-aware translation improvements, because these improvements affect only a few words in the translation of the documents. And indeed, we measure BLEU differences between models trained with different sentence position encodings that are negligible. Therefore, we adopt a more targeted evaluation in the form of accuracy on contrastive test sets for the disambiguation of context-dependent discourse phenomena. In particular, we use these 2 test sets for English to Russian and English to German. We start with the English to Russian language pair, and we train different 4-to-4 systems with the various kinds of encodings that we have seen previously. We add this encoding to the transformer in different ways. The vanilla strategy is to simply add the encodings at the input of the transformer, as we do with the other embeddings. In the persistent case, in green, we are adding encodings to the input of every block in the transformer. And in the yellow case, we are both adding encoding persistently, and we are also merging them into the same vector with position embeddings. The results show us that the vanilla concatenation approach 4-to-4 does not benefit of having extra information about the position of sentences in the sequence. In fact, all the systems but one underperform the 4-to-4 baseline. At this point, we hypothesize that the 4-to-4 concatenation approach is not encouraged to exploit sentence position encodings in the way we are training it. Therefore, we decide to adopt an alternative loss for training the 4-to-4 system, that is the context discounted loss that we have proposed recently. The context discounted loss is a modified version of the training loss that assigns less importance to the predictions of contextual tokens than the predictions of current sentence tokens. So it's a loss that pushes the model to stay more focused on the translation of the current sentence. This loss has been proved effective in many domains and language pairs, and it's a loss that pushes the model to distinguish between the different sentences that are present within the sequence. We hope that this loss will encourage the model to exploit sentence position encodings. Indeed, when adopting the context discounted loss, we see improvements above baseline, especially when the sentence position encodings are persistent. So here, the green and the yellow bars. In the case of sinusoidal segment embeddings, we only see improvements where these segment embeddings not only are persistent, but they are also fused with position embeddings, with PSE. And this is because, as expected, the model can't distinguish sinusoidal position and segment embeddings if we simply add them together. The best concatenation system that we have trained is the one that adopts segment-shifted position embeddings. This system compares favorably to other systems proposed in the literature in exactly the same experimental settings as ours. However, these results could not be transposed to the English to German language pair. We thought that the reason was that we were training with less data. Therefore, we increased the volume of data to match the one used in English to Russian. But even in this case, the concatenation approach trained with the context discounting will not profit from the extra information provided by sentence position encodings. More empirical efforts are needed to precisely define under which condition sentence position encodings can help the concatenation approach train with context discounting. Thank you for listening.